Step into the future bright and bold. With TaebiLab where stories unfold. Discover the magic research we unfold. TaebiLab, where science takes hold.
Welcome to the Deep Dive. Today we're getting into something really critical in cardiovascular health.
Yeah.
We're talking about computation meeting the heart.
Yeah, and the stakes are just so high. I mean,
Right.
you look at the projections, right? The U.S. Census Bureau figures suggest potentially 17.5 million new cases of serious CVDs between 2025 and 2060, heart failure, things like that.
That's a staggering number. It really underscores the need for, well, better monitoring tools. Faster, cheaper, more accessible.
Exactly. And that's why this whole deep dive is focused on understanding how we interpret the heart's mechanical function, specifically using those vibrations on the chest surface, seismocardiography or SCG.
Right. And just a quick note for you listening, if you want the real basics on SCG itself, what it is, how it works fundamentally, we covered that pretty thoroughly back in episodes 1, 5, and 6. Definitely check those out.
Good point. Because today we're really moving beyond the what and into the how. Like, how do researchers actually take the, complex little vibrations
Tiny vibrations, yeah.
and turn them into useful predictive clinical data?
So we're leaning on a specific source today.
We are. We're diving into a really important comprehensive review article. It's work published by researchers, including members of our own group, actually. It's pretty much essential reading if you're in this field.
Okay, let's get into it. What's the paper?
It's titled Computational Modeling of Cardiovascular Induced Chest Vibrations, a Review and Practical Guide for Seismocardiography Simulation, published in the International Journal for Numerical Methods in Biomedical Engineering, just came out in 2025.
Got it. And the authors who put this guide together.
So the lead author is Mohammed Ali Monfared. He's a PhD student right here in our group. Then there's T. Gamage and Ali Loghmani, who are external collaborators we work with, and Amir Taha Taebi.
Great. So this paper sets the stage, and the core tool we're discussing is finite element modeling.
That's right. FEF, pronounced FEM. That's the key. Our mission today, really, is to show you how this review positions FEM as the tool to transform the chest into like a personalized diagnostic system using SCG.
Okay, let's unpack that. FEM. When you're looking at these tiny heart vibrations, why isn't just measuring them directly enough? Why bring in this heavy-duty modeling?
Well, because the source signals the heart's movements are incredibly complex. You've got valves snapping shut, the heart muscle contracting, blood momentum shifting. All these things happen inside.
And that signal has a long way to travel, right?
Exactly. Through bone, muscle, fat, skin, before it even hits the sensor. So FEM is crucial because it lets us build, essentially, a high-fidelity digital twin of the patient's thorax.
A digital twin. I like that. So it's not just the endpoint vibration. You can model the whole journey of the signal.
Precisely. We simulate how those forces inside the heart propagate outwards. And the real magic of that simulation is sensitivity analysis.
Okay, what does that mean in practice?
It means we can digitally test what-if scenarios. What if this patient has thicker chest tissue? What if their bones are stiffer? We can isolate how specific patient characteristics affect the final SCG signal we measure.
Can you give us a solid example? Something FEM helped clarify.
Yeah, a really significant one highlighted in the review is about soft tissue thickness.
Yeah.
Think about patients dealing with obesity. The FEM simulations showed that just a 1 centimeter increase in chest soft tissue,
Just 1 centimeter.
yeah, just 1 centimeter, can slash the SCG vibration amplitude. We're talking by a factor of 2 for the first heart sound, and even worse, maybe a factor of 3 for the second heart sound.
Wow, that's huge.
Yeah.
It immediately tells you that what looks like a normal signal in one person might actually be a really weak, problematic signal in someone else just because of their body composition.
You've got it. You absolutely cannot interpret the signal without that physical context. FEM helps us separate what's maybe a change in the heart's mechanics versus what's just, the signal getting muffled on the way out.
Okay, what's another example?
Another great one is aging. We know tissues generally get stiffer as people get older, less elastic.
Right, which you can tweak in the model using something called Young's modulus, sort of a proxy for stiffness.
Exactly. So researchers used FEM to simulate increasing the Young's modulus of the chest tissue. And what they found was, interesting, the overall size, the amplitude of the SCG peaks actually went up. Stiffer tissue seems to transmit the force better.
Okay, higher peaks. But what about the timing?
And that's the crucial part. The timing of the key events, like when the aortic valve opens or closes, those so-called fiducial points, that timing didn't change at all with the stiffness. It was completely unaffected.
So that's the key separation. If you're hunting for disease markers, you need to know if a change in the waveform is the disease or just, the patient getting older. FE points towards timing features being potentially more robust indicators regardless of tissue stiffness.
Precisely. It helps isolate those mechanical event timings.
Okay, so FEM is clearly powerful for handling patient differences.
Yeah.
But this review isn't just a cheerleader for it, right? It sounds like it also lays out the difficulties, the trade-offs involved in building these digital twins accurately.
Oh, absolutely. It's very much a practical guide, warts and all. The biggest tension, really, is realism versus computational cost. Getting it right is hard, and it's especially tough in two main areas: the geometry of the model and the material properties you assign to the tissues.
Let's start with geometry. I mean, the body's 3D, so you'd think a 3D model is the only way to go.
Ideally, yes. But early on, many models used simplified 2D representations, mainly because they were just faster to compute, less demanding.
Easier on the computers.
Much easier. But the review really hammers this point home. SCG is fundamentally a 3D phenomenon. The sensor measures vibrations in 3 directions: up, down, left, right, front, back. And those waves don't just travel in straight lines inside the chest.
So what gets lost in 2D? What are you missing?
You miss all the complex spatial stuff. How a wave bounces off the sternum or gets absorbed differently by the lungs compared to the liver, for instance. These reflections, absorptions, boundary interactions, they fundamentally shape the vibration pattern that reaches the surface.
So a 2D model might just give you the wrong pattern entirely.
It can lead to imprecise or even incorrect predictions of the vibration. The review makes it clear. If you want real-world accuracy, you basically have to bite the bullet and go 3D, even though it takes way more computing power.
Okay, so 3D geometry is a must. Now, you need to feed that model the right information, the inputs. You call them boundary conditions.
That's right. And this is super tricky. To make the digital twin patient-specific, you need the actual motion of that patient's heart as the input signal driving the model.
Where does that come from?
Usually from high-quality medical imaging. We're talking 4D cardiac CT or MRI scans 3D images over time. But getting that data and mapping it correctly onto the digital heart model, that's a challenge.
What makes it so hard? Synchronization?
Synchronization is part of it, yes. And accurately translating the observed motion of the heart muscle and the blood volumes into, well, physical forces that you apply inside the computer model, it's complex.
So if the initial scan is imperfect or the mapping is off?
Garbage in, garbage out, as they say. Any inaccuracies there just cascade through the simulation and undermine the final result. It's time-consuming work, often needs a lot of careful processing.
Okay, 3D shape, accurate heart motion input. What about the stuff in between? The tissues. You mentioned material properties earlier.
Right. We talked about stiffness with Young's modulus, but real biological tissue isn't like, say, steel. It's way more complicated.
How so?
Well, for one, tissues like muscle and bone are heterogeneous, made of different components. And critically, they're viscoelastic.
Viscoelastic. Okay, what does that mean practically?
Think of it like this. A simple spring is elastic. It stores energy and gives it back perfectly. But biological tissue is more like maybe silly putty or dough. It has viscosity too. It dissipates energy. It acts like both a spring and a dampener, like a shock absorber.
And its stiffness might depend on how fast you push on it.
Exactly. That's rate dependence. Its behavior changes depending on the frequency or speed of the force. When that heartbeat wave travels through the chest, the viscoelastic tissues absorb and dampen some of the energy.
But models often simplify this.
Many current models, again, often for computational speed, treat tissues as purely linear elastic. Simpler, faster, but they don't capture that energy loss, that damping, or the rate-dependent behavior very well.
Which means the predicted vibration at the surface might not match reality, especially the amplitude.
Precisely. Modeling that complex viscoelastic behavior accurately is still a really significant ongoing challenge for the field. Getting those material properties just right is tough.
Okay, so this review really maps out the power of FEM, but also the significant hurdles: geometry, inputs, material properties. Synthesizing all this, what's the big picture? What's the roadmap forward that, our group and others are looking at?
The ultimate goal, the path forward, is really the pursuit of that truly personalized, highly detailed 3D FEM digital twin. We have to move beyond the simplifications.
Meaning more complex models?
Yes. We need comprehensive models that don't just include the heart and chest wall, but also the surrounding organs, lungs, liver, maybe even the diaphragm, because they all play a role in how those waves travel, reflect, get absorbed. It all matters.
And once you have this super detailed, validated twin of a healthy person, then how does that translate to clinical benefit?
That's where the real payoff comes in. Systematic pathology simulation. Once you have confidence in your healthy digital twin, you've checked it against real data, you can start digitally introducing specific diseases.
So you can simulate disease states safely in the computer.
Exactly, ethically safely. You can model, say, a thickened heart wall, like in hypertrophy, or simulate a valve that doesn't open properly, or model a hole between heart chambers, a septal defect.
And then see what the model predicts.
Precisely. Predict exactly how that specific pathology changes the SCG waveform that you'd measure on the surface. This predictive power is how we identify reliable, disease-specific biomarkers in the SCG signal.
So you could potentially say, this specific delay in the aortic valve closure timing, coupled with this change in amplitude, our model shows it strongly corresponds to moderate aortic stenosis, something like that.
That is absolutely the vision. It moves SCG from just being a general vibration measurement to becoming a sophisticated, predictive, truly patient-specific diagnostic tool. It uses that computational foundation to anticipate and classify disease.
It really sounds like this review is laying the groundwork for how computational science is going to revolutionize non-invasive cardiac monitoring.
It really is. It consolidates so much complex information and points the way forward. It's a landmark piece of work.
A definite milestone. #tagoutro.
It is, but if there's one final thought for you to take away and maybe mull over, it's this. The biggest challenge, perhaps, is always bridging that gap between the simulation and reality.
The digital twin and the actual patient.
Exactly. The absolute key to unlocking the clinical power of FEM is rigorous, detailed, subject-specific validation. We have to be sure that our digital predictions consistently match the physical reality of each patient.
That validation step is crucial. The model needs to prove itself against the real world.
That's the final hurdle for true clinical integration, ensuring that trust.
Modeling proposes, reality disposes. A great thought to end on.
Indeed.
And finally, just a required acknowledgement. This deep dive was created by generative AI using material provided by the TaebiLab.
Thank you for joining us today as we explored the computational future of monitoring the heart.
We dive into